Hi everyone. Here we present PostoMETRO, Pose Token Enhanced Mesh Transformer for robust 3D human mesh recovery. Current 3D human pose and shape estimation models can usually achieve good results on standard benchmarks, but tend to produce inaccurate human meshes in the wild occlusion scenarios, such as the target human body is occluded by persons out of interest or random object, limiting their further application. We studied the training and testing datasets and found that there's a clear difference between the training and testing images. As you can see below, the training images are often taken indoors. They usually have accurate 3D annotations, but there's no object or person occlusion. So, they're different from real-world images. On the other hand, the testing images are taken in natural settings. They usually have complex occlusion and environments, but they don't have 3D annotations. Given the observation we made, our motivation is natural and simple. Our main idea is to leverage external knowledge to mitigate the domain gap. In this work, we use 2D pose knowledge from 2D estimators. Considering 2D estimators can output accurate 2D poses on outdoor images, they can naturally offer human pose knowledge for 3D HPSE models, even under the wild scenes. Therefore, we add 2D pose knowledge from pre-trained 2D pose models into 3D HPSE models, expecting it will lead to better performance of 3D HPSE models. There are some related works which also propose to improve 3D HPSE models' performance by leveraging 2D poses. Pose 2 Mesh is a classic work using 2D poses for 3D human mesh recovery. It leverages 2D pose coordinates and converts the 3D HPSE task into two easier tasks, namely 2D pose to 3D pose and 3D pose to 3D mesh. It is effective, however, it ignores the image features, which can be very useful in disambiguating depth. 3D CrowdNet is another work that uses 2D poses. It uses 2D poses to calibrate CNN feature maps. After that, it constructs 3D poses from 2D poses and combines them with image features for 3D human mesh. The overall pipeline is simple yet effective, however, it is designed only for crowded scenarios, meaning that it might only improve cases when person occlusion occurs, limiting its further application. Inspired by the previous works, we can establish our initial model paradigm, as shown in the figure on the right side. To mitigate the domain gap, we represent human poses as tokens and use them to enhance 3D human mesh transformers. Different from Pose 2 Mesh and 3D CrowdNet, we bypass intermediate representation and use 2D poses as tokens in an end-to-end manner. This end-to-end manner enables our method to utilize 2D pose knowledge under different occlusions. Here we show the diagram of the overall model architecture. As you can see, we first pre-train a pose tokenizer in a WACV style, so that we have a codebook where 2D pose knowledge can be explicitly stored within. The pose tokenizer takes an RGB image as input, outputs a sequence of pose tokens extracted from the codebook. These pose tokens are then concatenated to a sequence of image tokens, which are flattened 2D image features produced by CNN. Those tokens are then fed into transformer encoders with camera tokens. Our transformer decoder takes joint tokens and vertex tokens as input, which are basically two sequences of learnable embeddings. After tokens are processed by transformers, a 3D coordinates regressor made by MLP converts token features into coarse 3D coordinates. The coarse 3D coordinates contain about 500 vertices, and a pre-trained mesh resampler then converts the obtained coarse 3D mesh coordinates into the final fine mesh, which is made up of about 6,000 vertices. The experimental settings of our works are quite simple. As for training datasets, we use Human 3.6M, UP 3D, Muco 3D HP, COCO, and MPII. It is worth mentioning that we also use pseudo 3D annotations for COCO and MPII datasets. When evaluating our models on the 3DPW test dataset, we also train our model on the 3DPW train dataset. When evaluating our models on the 3DOH test dataset, we also train our model on the training split of the 3DOH dataset. During our training, we only use color jittering, random rotation, and scaling as augmentations. As for image size, we fix our image input size to 256 by 256. We categorize different baselines into 3 types. Image-based indicates those baselines only take image as input, 2D pose-based indicates those baselines only take 2D poses as input, and mixed-based means that those baselines take both image and poses as input. Here we show some experimental results of our model. As you can see on the right side, despite that our method is indeed inferior to MPT and virtual marker on MPJPE, it beats all baselines significantly on MPVPE and PAMPJPE, showing the capability of PostoMETRO on the in-the-wild dataset. Here we also show the performance comparison on occlusion-specific datasets. As you can see, on 3DPW OCC, PostoMETRO with HRNet backbone outperforms other SOTA methods, including those targeted for occlusion scenarios, such as PEAR and NICI. On 3DOH, a similar superiority can also be observed. These results on different datasets show the robustness of our model under the challenge of object occlusion. On 3DPW PC, PostoMETRO still shows competitive results. Despite that our method is inferior to 3D CrowdNet on MPJPE, it still outperforms all methods on MPVPE and PAMPJPE. Note that 3D CrowdNet also underperforms PostoMETRO on object occlusion datasets. Despite that we do not manually design any components for different occlusion, namely object occlusion or person occlusion, our method can handle them equally well, distinguishing it from previous works. Here we show some qualitative results. We test FastMetro and our method on 3DPW and OC human datasets. As shown here, we observe that our model captures information about occluded body parts, such as limbs, as highlighted in the red rectangles. This shows the benefit of 2D pose tokens for enhanced 3D mesh reconstruction. We also conduct occlusion sensitivity analysis on our model. Here, as shown in Figure A, occlusion sensitivity analysis basically slides an occluder over the image, lets model take that corrupted image and regress the body pose, then computes the average 3D joint error with respect to ground truth. The heat maps in Figure C illustrate a method's sensitivity to a square occluder centered at each pixel location, where the warmer color indicates a higher error and the colder color indicates a lower error. The bar chart in Figure B demonstrates how much the error is per joint. As you can see, the model without pose tokens yields higher error at every joint, showing that the pose tokens can act as useful hints for a 3D mesh reconstruction model. Here we offer some essential ablation studies. The first table shows the effect of different tokens. We train our model with different types of tokens, namely image tokens and pose tokens, and test each variant on 3DPW OCC, 3DPW PC, 3DPW all, and 3DPW test. It can be seen that combining pose and image tokens always improves results. Such consistent benefits across various occlusion scenarios highlights the general applicability of our method. In the second table, we verify the effect of tokenization. Here we follow 3D CrowdNet and sample image features from 2D joint locations. We replace pose tokens with these features for training, yet get inferior results, which can be attributed to the high-dimensional property of tokens, showing the effect of tokenization. In the third table, we test the effect of WACV-style pre-training. Here, we try other pose tokens, such as embedding 2D pose coordinates from 2D pose predictors into tokens. We train this 2D coordinates variant using the same datasets for the same training time, including pre-training. The results show that such training might not guarantee the effective encoding of 2D pose knowledge, validating the importance of WACV and its pre-training. Furthermore, we ablate the generalizability of pose tokens. Representing 2D poses as tokens enables us to inject 2D pose knowledge into other architecture on the fly. Here we add 2D pose tokens to Metro by simply concatenating them to the original token sequence of Metro, training both it and the original Metro for 50 epochs. It shows the generalizability of 2D pose tokens, validating their ability to plug and play. We also ablate the choice of modulator. The best results are obtained when MLP mixer is used for pose tokens and a 1x1 convolution layer is used for image tokens. Besides multiplication across channel dimensions, MLP Mixer uses shared weights for all channels to do multiplication on spatial dimensions, hence better exploiting the spatial information. However, given the variability of the human body locations in images, using shared weights spatially can spoil image features. This explains why different modulators are needed for different modalities. Lastly, it is worth mentioning that we also set up a free online demo at Hugging Face, where you can upload your own image and get real-time inference results of PostoMETRO. Welcome to try it out. And that is all. Thanks for listening.